Okay, cool. So start. So the first question, do you know at what point the pH equals the pKa? Any idea? I mean, it's okay. Okay, cool. When the HA concentration equals the A minus. Exactly. So you got your Henderson-Hasselbalch equation where it's pH equals pKa plus log of A minus concentration over the HA. So in order for pKa to equal pH, that means this log term would have to go to 0 and log of 1 equals 0. So the only way to get A minus over HA to equal 1 would be for them to be equal, because the number divided by itself. That's how that math works out, but just in case you were wondering. So the second question, and this one, I think this worksheet's a little shorter in terms of content, I think, because I split up the last lecture into 2 parts with the buffer lecture 19 and then lecture 20 would be on Friday, because I realized if I did it, I wouldn't have enough material. So what is the pH of a buffer composed of 1.35 molar acetate and 3.5 molar acetic acid if the Ka, oh wow, that's not supposed to say ammonium, of acetic acid. Wow, I thought I changed that. Is 1.75 times 10 to the negative 5. So the first step, do you know the first step at all? Yeah. Okay, so you're going to take the negative log of 1.75 times 10 to the negative 5. And that's going to equal like, oh, I don't have my calculator. It should be like usually like 4 point something. I know that for a fact. 4 point something. Maybe I should keep it long ways because I think it's larger if it's long ways. So negative log 1.75 is 4.76. Oh, that's a quick. Okay, so your pH equals 4.7 plus log of A minus, whatever concentration of these here. Oh, hello. We're just doing the lecture 19 worksheet on D2L. It's called lecture 19 buffers. There's 2 lecture 19 worksheets on D2L under the SI section. One of them is buffers and salts, or salt and buffers. This one's just buffers because it's the latter part of the lecture 19. Yeah. And also there's a small mistake in the second question. It should say the Ka of acetic acid, not ammonium, because that's the right Ka, it's just the wrong name. Okay. So what is the A minus? Which one is that? Is that acetate or acetic acid? So then your HA is acetic acid. I know like some people get that confused. Like I remember somebody told me that they thought that A was acid because A for acid, but that's not it. So pH equals 4.76 plus log of 1.35 molar over 3.5 molar. And you should get a good answer. Okay, so you're going to get 4.35 as your new pH, or the pH of your buffer. So looking at this answer, does this answer look correct? Anybody? Look right? Okay, it does. And the reason why it looks correct is because if you look at the pKa value, it's 4.76. And your pH value is lower than 4.76. And it should be because your acid concentration is 3.5 and your base concentration is 1.35. So your acid concentration is greater. That means the pH of your buffer should be less. So like if you ever wonder, like, did I do that right? Did I accidentally flip acid and base? You can know, like, if you add base to a buffer, or not, this isn't really adding base to a buffer, but if inside your buffer you have a greater acid concentration than base, that means your pH should be lower than pKa, and vice versa. So if you ever want to like check yourself, like, oh, maybe that doesn't look right. Okay. So what would be the pH after the addition of 0.5 molar HBr? Okay. So I actually learned a trick via watching Dr. Baker's videos. I guess I always forgot, or I never really knew that you could just subtract the concentration. I always thought you needed like volume, but I was wrong. So yes. Okay. So here's your formula. But first of all, is based on top, bottom with KB. Yes. That is if you're solving for POH. POH, that would be POH equals PKB plus log of acid over log over base. But you don't need to use that. That'll only like confuse you. So I wouldn't worry too much about if you're solving for pH. If you're solving for pH, if you're given KB, then just get your Ka from KB, because it's going to be like a lot more difficult conversions if you try to solve it differently. Yeah, just use KB to find Ka. You'll like save your life. Okay, so which substance is HBr going to react with first? Is it going to react with acetate or acetic acid? Anybody know? Is HBr going to react with? Yes, it's going to react with acetate because it's an acid that's going to react with the conjugate base. So you have HBr. That's important when knowing how to set up your equation. So HBr plus acetate, and it's a reaction arrow, gives you CH3COOH, acetic acid, plus Br minus, which we're not really concerned with. So your HBr concentration. Wait, this is your ice. I think we can just use ice here because technically we're not converting to moles here. So I guess ice works. If that confuses anybody, please let me know. So, but technically there's no equilibrium. So okay, I'll just use SRF for our intents and purposes. So you have 0.5 m, and you start off with 1.35 m acetate and 3.5 m for acetic acid. So you're going to subtract 0.5 m. So here, you always, like again, it's like with ice tables, you always subtract from the reactants, add to the products, but also like, I don't know if you guys will ever see problems like this, but like you also always subtract the one that's less. That makes sense. Because you need like let's say if HBr was more, that means this essentially would mean you killed your buffer. So you would subtract your acetate from that, and then you'd end up. I wouldn't focus too much on it. I shouldn't have mentioned it, but you would, if you ever get confused. But that would be like a completely different scenario, which I don't think you guys need to know for this type. I think I did that right. And oops, sorry, it's plus. So when solving for your new pH, does pKa change? Does anybody know if pKa changes? No, never does, ever. It will never change. Because your Ka value is it's a quality. There's a better word for that, but I can't think of it. So it's like something that is a part of that compound. Like that is your Ka. It's like density. It doesn't change. That's always the way it's going to be. So solving for pH equals 4.76 plus log of now your new concentration of base. So 0.85 molar over your new concentration of acid. And that will equal 4.08 or 0.9 is probably better. And this makes sense because the pH of your buffer was 4.35. So that means the pH after adding acid should be lower. So like again, if you ever want to like verify, oh, did I do that correctly? Like check your pH. Like, does this make sense? And now we're doing the same thing, but for NaOH. So what species is NaOH going to react with? Going to react with acetate or acetic acid? Cool. Acetic acid, yes. So you have NaOH plus acetic acid going to react with to form okay. So you have 0.5 molar of NaOH. I think it was 3.5 molar of acetic acid and 1.35 molar of acetate. And you don't count these. They don't really affect anything. They're spectators. So you're going to subtract 0.5 molar from the reactants. Oh yeah, technically it's not I-stable, it's SRF. And add 0.5 molar to the product. So now your pH will be, so pH equals 4.76 plus log of your, oh, I didn't finish, sorry. So 0, 3 molar, and 1.85 molar. So log of your base over your acid. So 1.85 molar over 3 molar. And that will equal 4.55, which makes sense again because it is greater in pH than the pH of your buffer, which was like 4.35. So that makes sense. And also, the reason why there is such a change is because the ratio of acid to base is what's changing. So that's what's causing your change. So it's either getting bigger or smaller. So like if you're adding base, the ratio is getting smaller. If you're adding acid, the ratio is getting bigger. Yes, yeah. Okay. So what would be the pH of the buffer after adding 1 mole of HI to 0.085 liters of the buffer solution? So what's the first step? Or what's different about this calculation versus the ones before? What do you have to do to the acid and base? Yeah. So the concentration of acetic acid is 3.5 molar. So in order to find moles, you got to multiply that by 0.85 liters to give you 2.975 moles. And do the same thing for acetate. 1.35 molar times 0.85 liters equals 1.1475 moles. So now you can set up your SRF table, but first, what is your HI going to react with? Which species? I think it doing something funny, the screen. Well, not for my screen, but I think for you guys it looks weird. Does anybody know what HI is going to react with? Yes. Okay, so HI plus the acetate going to form acetic acid plus I minus. So now SRF, and you have 1 mole and 1.1475 mole and 2.975 mole. and you're going to subtract 1 minus 1 plus 1. So you're going to have 0 here. You're going to have 0.1475 mole here and 3.975 mole here. So for this problem, there is no, I guess, specification that what I added was a liquid. So there's no change in the volume. So like, let's say I just dissolved some salt, like not HI salt, but like solid HI. I don't know if that exists in real life, but perhaps it does. I'm pretty sure it does. So there's no change in volume. So if there's no, or technically, even if there was a change in volume, for this type of calculation, you don't necessarily have to find the concentration again, because the concentration of your acetic acid and acetates is the same. So if I have 1 divided by 2 over 3 divided by 2, ultimately I'm just going to end up with 1 over 3. So if I divide them both by the same thing and then divide one by the other, it's the same as just taking the numbers themselves and just dividing them by each other. There's no need to find concentration because it's going to be the same ratio between the two. Hope that makes sense. So I'm not going to change it back to concentration. I'm going to leave it as moles. This might help if you are you need all the time you can get on a test. So like, let's say like, oh man, you're trying to figure out, oh, what's the change in volume. If you don't want to do that, or if it's too much for you, or if it takes too long, or you feel like you're going to mess up and then you're like confused. It only matters when you're trying to find, I guess it matters with strong acid, strong base. That's what I saw. Because then you have your H3O plus OH minus goes to the 2 waters. That's when it matters. You have to change it back. But in this case, you don't, because it's going to end up giving you the same number regardless. If you don't believe me, you can try it. So your pKa is 4.76 again, plus log of your base, 75 over 3.975 will give you going to give you 3.32. Let's just do 3.3. So that's your pH. So quite a drastic change because you almost completely used up your conjugate base. Okay, so what could we do to this buffer, the buffer that we've been working with? What could we do to make it more effective? What's something we could change? Anybody know? Anybody? Yes, exactly. So if we increase the concentration of your acetate, making it closer to 3.5, we'll get a stronger buffer. So the buffer will be able to be more effective and more effective at controlling the change in pH. So the change in pH is not going to be as drastic as if when you have the concentrations that are like at a greater ratio from each other. So like having a 1-to-1 ratio of acid and base is really the best thing you can do for a buffer. Okay, so this would be HA to A minus equals 1. 1 to 1. Okay, so what is the molarity of 100 ml of strong base added to 0.53 liters of 1.35 molar ammonia to make a buffer solution of pH 9.7? So this one's a little tricky, but it's kind of like the same thing. It's just that instead of solving for pH, you're solving for the concentration of NH3 or your strong base, which is incidentally going to be equal to the concentration of NH3, if that helps. So I'm not entirely sure if you guys will see problems like this, but I know for a fact that I did when I took this course, and knowing how to set it up is really crucial, because there's one spot where you can make a mistake and it just will throw off everything, and it's a very easy mistake to make. So first, what I'm going to do is take or write the equation. So your pH is 9.7, and your pKa is 9.25 plus log of your A minus over HA. So one question I want to ask you guys before we start is does your H, after you add your strong base, does your HA concentration still equal 1.35? Or does your acid concentration, does it still equal 1.35 after you add your strong base? No, it does not. It's less. So how do we account for this? It's technically, so like let's say we rewrite HA. Instead of writing HA, we write NH4. And let's change A minus to X. So how are we able to, I guess, get rid of this change? It's by, you got to take into account the fact that the moles of NH4 are going to be consumed. So you got to subtract NH4 by X. So it seems a little more complicated, but that's technically how you would do it. If you did it without the minus X at the bottom, you'd get it wrong. It'd be wrong. So you have your NH4 concentration. So ultimately what I'm going to do is solve for moles, because they're going to end up having the same, well, moles is ultimately what matters when you're doing these titration reactions, or when you have acid reacting with base. Ultimately what you have to equate is moles. So I'm going to convert NH4 plus to moles, because that's going to be what is reacting with base. So technically, I guess if you have trouble understanding what I'm talking about, it would be like if I set up my SRF table and I had, let's say, NH4 on this side. Oh, that's not how that looks. NH4 plus your OH minus, which is just what we'll call a strong base. And then it goes to NH3. This would be whatever number it is, and it would be minus X, because you don't know quite what the moles are yet, and it'd be plus X. So ultimately what you get whatever the moles, NH4 moles, minus X, which is what you'd put in here, and this would just be X. So that's why, if that makes sense now. I'm gonna erase this all. Take my space. Okay, so first thing now would be to solve for moles of NH4, because even if I do add, like, this is the moles of NH4 that was initially in the solutions, what you're starting for, what you're solving for, because you're looking at what is at the start column of your SRF table. So before the base was added. So it's 0.53 times 1.35. which is 0.72. So 9.7 equals 9.25 plus log of x 0.72 minus x. And again, if you guys get confused as to like why I'm only using moles now, it's ultimately because their concentration, like it will just be like divided by the same number, like whatever it would be, 0.63 at the end, and that would cancel. So I don't include it. It would cancel, so I just don't include it. So you're just going to end up solving for x. So you're going to have 9.7 minus 9.25 equals log of x over 0.72 minus x. And that's just going to be, pretty sure, 0.45. Yeah. Equals, and I'm just going to go ahead and take the liberty and raise 10 to that power because it's going to save a step. That's going to equal x over 0.72 minus x. So 10 to the 0.45 is going to be 2.82 equals x over 0.72 minus x. So you're going to multiply the denominator on both sides to get it to cancel. So you're going to have 2.03 minus 2.82 x equals x. And then it's going to end up being 2.03 equals 3.82 x, and x is going to equal 0.53 molar. I mean, not molar, moles. But it did not ask you for your moles. What it asked you for was molarity. So you got to solve for molarity. So you know your moles, and you know that you had 10 ml added. So molarity equals 0.53 moles divided by 0.1 liter, which is going to give you, oh, that's not 0.1 liter, which is going to give you 5.3 molar. Yes. So it's a pretty strong base that you just added. Does anybody have any questions about that? Did that make sense? What I did? Okay. So what is the buffer range? Does anybody know what your buffer range is? Yes. And incidentally, you ended up also asking the, answering the second question or the second part. So yeah, the buffer range is 1 unit greater than the pKa and 1 unit less. It's that range. And pretty much it's just the range in which the buffer is useful. Like after that, it's no longer really effective. Like the pH is going to change very drastically. So yeah, that's what that is. So it encompasses your pKa. pKa is very important. So it would be, buffer range would be pKa minus 1 to pKa plus 1. Yeah. So if you want to make a buffer with a pH of 4.9, would it be better to use acetic acid or ammonium? So the pKa of acetic acid is 4.76, and the pKa of ammonium is 9.25. So which one's more effective? Yes, that would be your most effective buffer to use if you're trying to, because I guess at a point after like 8, that means it's almost like if you try to get your buffer of NH4 to 4.9, pretty much your buffer's already dead. So like you could essentially do it, but it's no longer a buffer at that point. It's just like an acidic solution. So if the solution contains 1.53 moles of conjugate base, how many moles of acid does it contain? So this is feeding off of this question before. So technically, in order to solve this question, you need to be able to solve that question. So you need to know which one to use. Would you be using ammonium, or would you be using acetic acid? But we already determined that we're using acetic acid. So it's telling you how many moles of conjugate base you have. And you know that the pH is going to be 4.9. So you do your pH equals pKa plus log of A minus over HA. Yes. So your pH is going to be 4.9. So you're referring back to the previous question where it says 4.9 is your pH. Okay. And your pKa of acetic acid, you know, is 4.76 plus log of, you don't know, you don't need to use your concentration again because they'll both have the same volume if they're both in the same solution. So you can just use moles. So your moles of conjugate base is 1.53, and you're solving for HA, which you don't know. So we'll just call that X. And we'll start to calculate again. Oops, sorry. Add more space. Don't think it's working with me. Okay. So you do the same thing. 4.9 minus 4.76 equals log of 1.53 over X. So 4.9 minus 4.76. 0.14. And I'm going to take the liberty and just take this to the raise 10 to that power. So 10 to that power equals 1.53, sorry, 3 over X. So wonky arrow. 1.38 equals 1.53 over X. Yeah, and this one's a little simpler because it told you that the buffer already equaled 4.9. You're not making a buffer, whereas before you were making a buffer from just weak acid. I think it was acid. Now this is already inside, so there's no reaction. It's just the buffer itself. It's just in there, so you don't have to subtract anything from the base because you're not adding acid to it. You didn't add acid to make a buffer. You already have the buffer, and you're trying to determine the ratio of moles based on the pH. So you got 1.38x equals 1.53. So equals 1.11 mole. And that's what they asked for. So, oh, I think the screen is weird. Okay. So that's what they asked for. So this would just be your, no, not concentration, your CH3COOH moles is 1.11 mole. So that's it for this worksheet. If you guys have any questions, anything you want me to go over again, please ask if anything that you don't understand, or even something that's not from this worksheet that you don't understand. Okay, so am I able to go over any homework questions? Yes and no. I can tell you how to do it or tell you or guide you in the right direction, but I cannot give you the answer. So let's see. About 3C without volume. Okay. Without volume given. I'm not entirely sure. Oh, she said 1 liter. Okay. Because I was like, I don't think I know this. But did you get that, Ben? That you just assume it's 1 liter? Because honestly, you couldn't do it without that. Okay, cool. Is that all the questions for homework? Okay, cool. So I think what I wanted to go over next was this list of concepts that I got here. So I posted this on D2L. I hope everybody can see it. Probably should turn it this way again. This is better. Yeah. So pretty much this is just going over, like the stuff that we learned. It's been checked and verified by your professor, so I don't think it should be too bad. So, like going over the products of strong acid, strong base, which is just, salt and an acid. I mean, salt and water, not an acid. No, salt and water. What is the definition of a salt? How to strong acid, strong bases dissociate. So so we just finished the lecture 19 worksheet. So this is pretty much all the stuff that you should know at this point. This is, I guess, because I understand completely how difficult online taking classes online is, especially for science classes. So if you need to keep up with your material at a good pace, so it's not because it's really difficult to pull an all-nighter at your house. I don't know about where you can't go out to the library or somewhere. Having to pull an all-nighter at home is really difficult because it's just why am I doing this when I could just sleep? But if you guys want to keep up with everything as you go by, I think it'll be a lot easier knowing some of these basic things just at every point. For this lecture, I mean, for this section, it's not as together, I guess you could say, as section 3. Section 3, everything built upon itself. But for this one, after you guys finish the titrations, it's kind of just going to drift off into entropy and stuff like that. Similar stuff to what you've done before, but a little more in depth. So I just want to let you guys know that this is a resource that you have on D2L. I posted it. So if you want to check it out, please do. You know, it's for you guys. I didn't make it for me, unfortunately. But you know, if you guys need help, still feel free to message me. There's still the group me. If you're not in the group me, you know, you can always join. I think it's posted in an announcement if you want to scroll through it and scroll through the announcements and add yourself, then it'd be easier for you to ask me questions that way if you need help. And you know, that's all I have for you guys today.